Hello everyone. In this stream, we are going to, talk about the Solidity and Uniswap V3. We are going to build a Uniswap V3, protocol. And anybody who has been, working in the blockchain for quite some time must be aware of this Uniswap V3 thing. I mean, it's sort of a, as one of my friends says, it's the sort of a creation definitely worthy of a Nobel Prize, right? Like, the the overall way the financial market works in a traditional system versus this way of doing, you know, creating these markets in a blockchain that is very accessible. And as you will get to know, like the concepts are also very simple. I mean, it's really mind-blowing thing. And part of my reason of doing this Uniswap V3 is I was like, I wanted to do this with Cairo, but unfortunately there are not many resources that are available to do this in Cairo. So my first goal is to do the same with with the Solidity, and then basically maybe in the future streams we convert this in Cairo. Uniswap V3, so the current Uniswap paper they published the Uniswap V4 as well. It is in the draft mode and the code is available. But to get started with the Uniswap V4, I mean, we need to understand the Uniswap V3. So that is also part of the reason that I'm doing this stream on Uniswap V3. More to for my personal learning than you know telling you guys. But yeah, I like this idea of building things in the open. And yeah, let's just get started. So in a nutshell, what this Uniswap thing is. So Uniswap is sort of a protocol for AMM, right? Automatic market makers, or basically the counterpart to the order based markets. If you have done any trading, maybe like Nasdaq, or in India BSE NSE, you must be familiar with the order based markets, order based bookings. So this is the counterpart to Uniswap, to that particular thing. And if you are not aware of the if you are not aware of the what what this AMM things are, and how they work, I'll be just adding this book link in the Notion page that I'll add into the stream. But we are not going to dive deep into the theoretical aspect of the AMMs. Our main goal is to build the Uniswap V3 protocol, and mainly the smart contracts, not even the not even the front end part. But yeah, okay. So let's see. We are going to focus this Uniswap V3 book. This seems like a very amazing resource. And this is like like I would say the best thing that is out there, apart from the Uniswap docs. So let's get started. Okay. So development environment, we are going to build two applications: an on-chain one, a set of smart contracts deployed on Ethereum; an off-chain one, a front-end application that will interact with the smart contracts. While the front-end application is part of this book, it won't be our main focus. We'll build it solely to demonstrate how smart contracts are integrated with front-end applications. Thus, the front-end application is optional, but I'll still provide it. So yeah, I mean the the idea of this stream is to go through this book together, and just to understand what is going on there. Quick introduction to Ethereum. Ethereum is a blockchain that allows anyone to run applications on it. It might look like a cloud provider, but there are multiple differences. You don't pay for hosting your application, but you pay for deployment. Your application is immutable. That is, you won't be able to modify it after it's deployed. User will pay to use your application. I mean, very clear and a very abstract definition. I mean, as somebody who's working in the Ethereum for a long time, I can definitely say that Ethereum is much more than that. But yeah, I guess it works for our purpose. To better understand these movements, let's see what Ethereum is made of. At the core of Ethereum and any other blockchain is a database. The most valuable data in Ethereum's database is the state of accounts. An account is an Ethereum address with associated data. So balance, the account see the balance code, bytecode of the smart contract deployed at this address, and storage, space used by smart contracts to store data. Nonce, a serial number that is used to protect against replay attacks. Okay. Ethereum's main job is building and maintaining this data in a secure way that doesn't allow unauthorized access. Ethereum is also a network of computers that build and maintain the state independently of each other. The main goal of the network is to decentralize access to the database. There must be no single authority that's allowed to modify anything in the database unilaterally. This is achieved by meaning of consensus, which is a set of rules all the nodes in the network follow. If one party decides to abuse the rule, it will be excluded from the network. Fun fact, blockchain can use MySQL. Nothing prevents this besides performance. In its turn, in its turn, Ethereum uses level DB, a fast key value database. Okay, that's interesting. Every Ethereum node also runs EVM, Ethereum Virtual Machine. A virtual machine is a program that can run other programs, and EVM is a program that executes smart contracts. Users interact with contracts through transactions. Besides simply sending ether, transactions can contain smart contracts called data. It includes an encoded function, contract function name, a function parameters. Transactions are packed in blocks and blocks then mined by miners. Each participant of the network can validate any transaction and any block. In a sense, smart contracts are similar to JSON APIs, but instead of endpoints, you call smart contract functions and you provide function arguments. Similar to API endpoints, smart contracts execute programmed logic. You can optionally modify smart contracts stories. Unlike JSON API, you need to send a transaction to mutate blockchain state, and you will need to pay for each transaction you are sending. Finally, Ethereum node exposes a JSON RPC API. Through this API, we can interact with a node to get account balance, estimate gas costs, get blocks and transactions, send transactions, execute contract calls without sending transactions. Here you can find full details list of available endpoints. Okay. Transactions are also sent through the JSON RP API, see each send transaction. Local development environment. There are multiple smart contract development environments that are used today: Truffle, Hardhat, and Foundry. Truffle is the oldest of the three and is the less popular of them. Hardhat is its improved descendant and is the most widely used tool. Foundry is the new kid on the block, which brings a different view on testing. While Hardhat is still a popular solution, more and more projects are switching to Foundry, and there are multiple reasons for that. With Foundry, we can write tests in Solidity. This is much more convenient because we don't need to jump between JavaScript and Solidity during development. Writing tests in Solidity is much more convenient because you have all the native features and you don't need a special type for big numbers and you don't need to convert between strings and big numbers. Foundry doesn't run a node during testing. This makes testing and iterating on features much faster. Truffle and Hardhat start a node whenever you run tests. Foundry executes tests on an internal EVM. That's amazing. Yeah. That being said, we will use Foundry as our main smart contract development and testing tool. Foundry Foundry is a set of tools for Ethereum application development. Specifically, we are going to use Forge, a testing framework for Solidity, Anvil, a local Ethereum node designed for development with Forge. We will use it to deploy our contracts to a local node and connect to it through the front-end app. Fast, a CLI tool with a ton of helpful features. Forge makes smart contract developers' life so much easier. With Forge, we don't need to run a local node to test contracts. Instead, Forge runs tests on an internal EVM. which is much faster and doesn't require sending transactions and mining blocks. Forge makes smart contract developers' life so much easier. With Forge, you don't need to run a local node to test contracts. Instead, Forge runs tests on its internal EVM, which is much faster and doesn't require sending transactions and mining blocks. Forge let us write tests in Solidity, and Forge also makes it easier to simulate state. We can easily fake our Ether tokens, Ether or token balance, execute contracts from other addresses, and deploy any contracts at any address, etc. However, we will still need a local node to deploy our contracts to. For that, we will use Anvil. Front-end applications use JavaScript Web3 libraries to interact with the Ethereum node. This is why we will need to run a local node. EtherJS is a set of Ethereum utilities written in JavaScript. This is one of the two most popular JavaScript libraries used in decentralized application environment development. These libraries allows us to interact with the Ethereum node via the JSON API, and they come with multiple utility functions that make developers' life easier. MetaMask, Ethereum wallet in your browser. It's a browser extension that creates and securely stores Ethereum private keys. MetaMask is the main Ethereum wallet application used by millions of users. We will use it to design transactions that we will send to our local node. React is a well-known JavaScript library for building front-end applications. You don't need to know React. You'll provide a template application. Forge will create a. Okay, so let's start with the project. Okay, so let me move my terminal. Move to Dell. Okay, so let me close this. Okay, and what I'll do is I'll bring this book in my second browser window. Okay. So that I have access to code every time you're doing something. Okay. Okay. So we are going to create a new project. Okay, mkdir, let's say uni v3 clone. Okay, uni v3 clone. Okay, Forge unit. Okay, so we have this, and let's do one thing as well. Let's create a GitHub repository, and we want to basically uh, put everything on GitHub as we build this thing in real time. So we have access to everything. Okay, let's create a new project. Uni v3 clone. Okay, I just need to copy this and get in it. Okay, let's say initial commit. Okay, and I guess we are done. And we have this. I want to update it. So what do we have here? So we have the Foundry toml file, default src, out, libs. Okay, we have the lib file. Lib does have a lot of things. Src contract. Okay, and then we have a test. Okay, so what do we need to do? First, we'll create simple contracts in src tests, and if you are using click to forge in it. Okay, that's okay. First, we'll create simple contracts in SRC, tests, and script. Okay. So we'll create our front end later. Hmm. Okay. So let's what we will build. Okay. Let's come back to. Let me close this. Let me close this as well. Uni V3 clone. Yeah. Okay. Okay. So for the UI part, we'll create it later. When we'll come to the UI part, right? Okay. Let's come to. Okay. What we will build. Okay. The goal of the build is to build. The goal of the book is to build a clone of Uniswap V3. However, we won't build an exact copy. The main reason is that Uniswap is a big project with many nuances and auxiliary mechanics. Breaking down all of them would bloat the book and make it harder for readers to finish it. Instead, we will build the core of Uniswap, its hardest and most important mechanisms. This includes liquidity management, swapping, fees, a periphery contract, a quoting contract, and an NFT contract. After that, I am sure you will be able to read the original source code of Uniswap V3 and understand all the mechanics that were left outside of the scope of this book. Smart contracts. After finishing the book, you will have these contracts implemented. Uniswap V3 pool. Okay, the core pool contract that implements liquidity management and swapping. After finishing the book, you will have these contracts implemented. Uniswap V3 pool, the core pool contract that implements liquidity management and swapping. This contract is very close to the original one. However, some implementation details are different and something is missed for simplicity. For example, our implementation will only handle exact input swaps, that is, swaps with known input amounts. The original implementation also supports swap with unknown output amounts when you want to buy a certain amount of tokens. Hmm. Uniswap V3 Factory, the registry contract that deploys new pools and keeps a record of all the deployed pool. This one is mostly identical to the original one besides the ability to change owner and fees. Uniswap V3 Manager, a periphery contract that makes it easier to interact with the pool contract. This is a very simplified extension of swap router. Again, as you can see, I don't distinguish exact input and exact output swaps and implement only the former and implement only the former ones. Uniswap V3 quota is a pool contract that allows calculating swap prices on chain. This is a minimal copy of the quota and quota V2. Again, only exact input swaps are supported. Uh, Uniswap V3 NFT Manager allows turning liquidity positions into NFTs. This is a simplified implementation of non-fungible position manager. Front-end application. For this application book, I also built a simplified clone of the Uniswap UI. This is a very dumb clone, and my React and front-end skills are very poor. But it demonstrates how a front-end application can interact with smart contracts using EtherJS and MetaMask. Okay, so we have four things. Okay, so what we are going to build is, okay, let me create a new readme dot md. So the first contract is Uniswap V3 pool. Uniswap V3 pool. Okay. And this contract basically implements liquidity management and swapping. Okay. The other thing is Uniswap V3 factory. Uniswap V3 factory. Okay, the registry contracts, the registry contract that deploys new pools and keeps a record of all deployed pool. Keeps a record of all deployed pools. Okay. The other one is Uniswap V3 manager. Uniswap V3 manager. It's a periphery contract that makes it easier to interact with the pool contract. A periphery contract that makes it easier to interact with the pool contract. Okay. And Uniswap V3 quoter. Uniswap V3 quoter. Calculate swap prices on chain. Right. Swap prices on chain. Okay. And Uniswap V3 NFT manager. Okay. Turning liquidity positions into NFT. Turning liquidity positions into NFT. Okay. So that is all. That is like the four things. Okay. Introduction. Okay. The first step. In this milestone, we will build a pool contract that can receive liquidity from users and make swaps within a price range. To keep it as simple as possible, we will provide liquidity only in one price range, and we will allow to make swaps only in one direction. Okay. Also, we will calculate all the required math manually to get better intuition before starting using mathematical libraries in Solidity. So what we are going to do is we are going to provide a liquidity in only in one price range, and we will allow to make swaps only in one direction. Okay. Also, we will calculate all the required math manually. Okay. Let's model the situation we will build. So there is an ETH USDC pool contract. So there is some amount of ETH and some amount of USDC. ETH, X amount of ETH and Y amount of USDC. We'll set the current price to 1 ETH is 5000 USDC. The range you will provide liquidity is 4545 to 5500 USDC. We'll buy some ETH from the pool at this point. You'll buy some ETH. So USDC price will buy some ETH. So ETH will be less, USDC will be more. So ETH price will increase. And we want the price of the trade to stay within the price range. Okay, so what this is doing, 1 ETH 5000 USDC, ETH USDC, current reserves. Okay, and end price, right? Okay, right. Buying as is the trade function is ETH minus USDC plus ETH into USDC, right? Okay. Before uh, before before getting to the code, let's figure out the math and calculate all the parameters of the model. To keep things simple, I'll do math calculations in Python before implementing them in Solidity. This will allow us to focus on the math without diving into the nuances of math and solidity. This also means that in a smart contract, we will hard code all the amounts. This will allow us to start with a simple minimal viable product. Hmm. Okay, let's open this notebook. Hmm. Import math, minimum tick, 887272, maximum tick, 887272, Q96, 2 to the power 96, eat 10 to the power 18, price to tick, P, method floor, method log P, price to sqrt, sqrt to price, tick to sqrt, liquidity 0, liquidity 1, calculate amount 0. Okay. Hmm. Okay. I mean, okay. Hmm. Hmm. Let's go. Hmm. 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 Calculating liquidity. Trading is not possible without liquidity, and to trading is not possible without liquidity. And to make our first step, we need to put some liquidity into the pool contract. Here is what we need to know. Here is what we need to know to add liquidity to the pool contract. A price range. Trading is not possible without liquidity, and to make our first step, we need to put some liquidity into the pool contract. Here is what we need to know to add liquidity to the pool contract. A price range. As a liquidity provider, we want to provide liquidity at a specific price range, and it will only be used in this range. Amount of liquidity, which is the amount of two tokens. We will need to transfer these amounts to the pool contract. Here we are going to calculate these manually, but in a later chapter, our contract will do this for us. Let's begin with a price range. Recall that in Uniswap V3, the entire price range is demarcated into ticks. Each tick corresponds to a price and has an index. In our first pool implementation, we are going to buy ETH for USDC at the price of $5,000 per ETH. Buying ETH will remove some amount of it from the pool and will push the price slightly above 5,000. We want to provide liquidity at a range that includes this price, and we want to be sure that the final price will stay within the range. We'll do a multi-range swaps in a later milestone. So we'll need to find three ticks. The current tick will correspond to the current price. The lower and upper bounds of the price range we are providing liquidity to. Let the lower price be 45.45, upper price is 5. From theoretical introduction, we knew that liquidity y upon x. Since we agree to use ETH as the x reserve, and okay, ETH as the x reserve and USDC as y reserve. Okay. Hmm. 70.71, 67.60, and 74. Here PC is the current price, PL is the lower bound of the range, PU is the upper bound. Now we can find the corresponding ticks. We know that prices and ticks are connected via this formula. Dollar square root of PI is equals to 1 point. Okay. We can find tick I via. Okay. Uh, huh. Okay. The square root in this formula But since we are working with you, we need to preserve them. Hmm. Log underscore log. Okay. Met dot log. Met dot log p. Hmm. Price to tick. Okay. Well, this is some bit of a complicated math. Mm-hmm. I equals to log 1.0.0001 p of I. Okay. So we got the upper tick and lower tick. The last thing to note is Uniswap uses Q61 number to store liquidity. Mm, mm. In the work calculation, prices are floating point numbers. Mm, Luckily, we need to simply multiply the number by mm, uh, mm, okay. Token amount calculation. Next step is to decide how many tokens we want to deposit into the pool. The answer is as many as we want. We can deposit as much as it is enough to buy us a small amount of ETH without making the current price lease level. How many tokens we want to deposit into the pool? The amounts are not, we can deposit as much as it is enough to buy a small amount of ETH without making the current lease the price range. And we need to mint any amount. So getting the amounts. So getting the amounts you want is not a problem. 1 ETH. Then of the current pool reserves tells the current spot price. Put token into the give the same price. Next, we want to calculate L based on the this is all tight. Okay, all this formula is for infinite curve. We want to put liquidity into a limited price range, which is just a segment of the infinite curve. We need to calculate L specifically for the price range. We are going to deposit liquidity into. Okay, we want to calculate AL based on the amount we will deposit. Into a limited price range, which is just a segment of that infinite curve. We need to calculate L specifically for the price range we are going to deposit. Depleted the amount of one token from price range and leave the pool with only another token. And we place only one token in the range. 4,500 to 45 to 5,500. We provide the liquidity at 5,000. So at 45, all the ETH will be gone. Right. Only one to one. When to find an L that will allow the price to move to either of the points. We want enough liquidity for the price to reach either of the boundaries. Thus, we want L to be calculated based on the maximum amount of X and Y. Delta X. Now let's see. In fact, prices are not defined at this point because there's only one reserves in a pool. You don't understand your reserve price amount. Let the price on the point be higher and then the price on the point is lower than the starting price. What are you saying? The prices are not defined at these points because there are only one reserve. Point B is the start price. Now break the curve from the image into two segments. This is ETH. Heading yeah, and providing okay. Cast from V. Okay, it works. So basically the idea is we got it. Okay, let's see. Okay, let me okay. Okay, now you learned from the introduction. Let's remove these contract first. Okay. Hmm. Okay, enough of the theory. Let's start coding. Create a new folder. Mine is called Uniswap V3 code. Run the 4-unit VSCODE in it. Okay, let's create our first contract. Okay, pool contract. Pool contract. As you learned from the introduction, Uniswap deploys. As you learned from the introduction, Uniswap deploys multiple pool contracts. That's correct. Each of which is an exchange market for a pair of tokens. Uniswap groups all its contract into two categories: core contracts and periphery contracts. Core contracts are, as the name implies, the contracts that implements core logic. These are minimal, user unfriendly, low level contracts. The purpose is to do one thing and to do it as reliably and securely as possible. In Uniswap V3, there are two such contracts. Pool contract, which implements the core logic of a decentralized exchange, and a factory contract, which serves as a registry of pool contracts and a contract that makes deployment of pools easier. We will begin with the pool contract, which implements 99% of the core functionality of the Uniswap. Create a Uniswap V3 pool. Okay. Contract Uniswap V3 pool. Let's think about what the data the contract will store. Since every pool contract is an exchange market of two tokens, we need to track the two token addresses, and these addresses will be static, set once and forever during pool deployment. Thus, they will be immutable. Every pool contract is a set of liquidity positions. We will store them in a mapping where keys are unique position identifiers and values are structs holding information about positions. Each pool contract will also need to maintain a tick registry. This will be a mapping with keys being tick indexes and values being structs storing information about ticks. Since the tick range is limited, we need to store the limits in the contracts as constants. Recall that pool contracts store the amount of liquidity L, so we will need to have a variable for it. Finally, we need to track the current price and the related tick. We will store them in one storage slot to optimize gas consumption. These variables will be often read and written together, so it makes sense to benefit from the state variables packing feature of Solidity. What is the state variables packing feature of Solidity? Layout of state variables in storage. State variables of contract are stored in storage in a compact way such that multiple values sometimes use the same storage slot. Except for dynamically sized arrays and mappings, data is stored contiguously items after item, starting with the first state variable, which is stored in slot 0. Each variable, a size in bytes, is determined according to its type. Multiple contiguous items that need less than 32 bytes are packed into a single storage slot if possible, according to the following rules. Yeah, I've come across this concept in Starknet and Cairo. I guess it's more or less the same concept. Okay. Uh, why it is leaving the definitions? Hmm. Okay. User B3 uses many other helper contracts in tick positions. And tick and positions are one of them. Uh, Part of the using A for B is a feature of Solidity that lets you expand type of B with functions from library contract A. They simplify managing complex data structure. For brevity, I will omit detailed read of me, don't hesitate. This is the book, I guess. Solidity. Hmm. Uh, Initialize some of the variables. Minting. Okay. So let's build this. So let's build this. New file. Uniswap V3 poll. Uniswap V3 pool.sol. Contract Uniswap V3 pool. Okay. New file tick.sol. Vision not sol. Tick struct info rule list. Okay. I don't think it will work. Okay, and position. — 128. Okay. Hmm. Okay. Info. Tick.info. Ubuntu. Token 0. Nothing. In 24. Mm. Mm. Hmm. Mm-hmm. Okay. Mm, mm, current price and tick. We don't need to provide liquidity for the latter. Yeah, starting on this everything with P calculated and hardcoded values. Insurity bonus address. V2 is called, the reason is that we and the video bonus contract. Where is the same name? Okay. Function mint lower tick amount amount 1. Mm, amount of notice that the user specifies L, not actual token amounts. Not very convenient, of course. Hmm. Okay. Hmm. Price range. Hmm. 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 नहीं. Oh. Hmm. The text update function is delta. Hmm. So basically what it is doing is, okay, as you have learned from the okay, very contract. Mm, uh, mm, mm. Mm. balances. Mm, okay, guys, I think this is the enough coding. Let's take a break and see you guys.